Okay, so moving on to our next question, we have piston cylinder in the figure below contains 0.1 kg of R410A at 600 kilopascal, 60 degrees Celsius. It is now cooled so that the volume is reduced to half the initial volume. The piston has upper stops mounted, and the piston mass and gravitation are such that floating pressure is 400 kilopascal. And we are asked all of these things. Again, they don't matter, we'll find them in the very end when we figured out all of the variables at all of the states. So let me draw the figure. There will always be an intermediate state, please remember. Let me draw what is going to happen, and then I will explain why that is going to happen. Right, at state 1 we are given the following: 0.1 kg of R410A at an initial pressure of 600 kilopascals and an initial temperature of 60 degrees Celsius. It is being cooled, so heat is being lost. And then finally, the volume V3 is half of V1. So I want you to think what will happen here. From where will the energy go first? First, will the volume start suddenly decreasing, or will the pressure decrease and then the volume decrease? If you see carefully, it is given to us in the question that the floating pressure is 400 kilopascals. So the volume cannot immediately decrease, right? Because 600 kilopascal pressure is already there. So it stands to reason that first our pressure will reduce, and then once pressure has reached 400 kilopascal, the piston will start coming down and the energy will go away from the volume. So a 400 kilopascal intermediate state will be reached, where this will just drop, at some T2 after heat has been lost, and V2 is the same as V1, because remember, first energy is going away from the pressure so that the piston is able to come down, and then after piston has come down, it will go till half the volume. So P3 is still 400 kilopascals, because now the energy is going away from the volume, not from the pressure. And V3 has been given to us as half of V1, and T3 we do not know. So 1 to 2 is a constant volume process, because energy is going away from the pressure so that the pressure will come down to 400 kilopascals. And 2 to 3 is a constant pressure process, because energy is going away from the volume and the volume is getting halved. Right. So let us find all of the variables at the given states at 1. Is it given to us already? Okay, no, right now it's not given, right? So here at 1 also we'll have to find what is going on. So pressure is 600 kilopascals and temperature is 60 degrees Celsius. Let us work with the pressure and draw the TV diagram. Remember, opposite diagram is drawn. So at 600 kilopascal of pressure, our T sat will come out to be, from the tables, let us just refer to the tables, sorry. R410A, we have to go to the R410A tables. Always a pain to scroll tables. I wish I had the physical copy of this, it would be so much easier. But then I guess I won't be able to show you what I'm doing. So I guess it's fine as well. Yeah, here we are. At a pressure of 400 or 600 kilopascals, we do not have the exact value. We have 573 and 678, neither of which are very close. So let us switch to working with the temperature. If we are working with the temperature, we'll have to draw a PV graph. Or wait, this will be a good opportunity to show you what to do when our exact pressure is not given, right? So let us go back to the tables. And if we see in the saturated R410 tables, our pressure is either 573 or 678. We don't have a 600 kilopascal entry. However, if you remember, in the superheated tables, our very first row would tell us the value of the saturation temperature, right? So let us go down to the superheated tables and see 50 kilopascal is there, 100 is there, and if you keep going, you will find 600 kilopascal as well. And this value, the one in the bracket beside 600 kilopascals, will give us the value of saturation temperature. So we can either draw a PV graph, the opposite graph at, this is what, 60 degrees Celsius, I think, yeah, and then find the value of saturation pressure and then see where our given pressure is and saturation pressure is and all that. Or what we can do is we can draw the TV graph and at the given pressure of 600 kilopascal get the value of saturation temperature from the superheated tables and then use that. So which is what we're going to do right now. So as we see from the superheated tables, our saturation is minus something, right? It doesn't matter, it's in minus. So very clearly our given temperature is much higher, so it is a superheated vapor. So we will use a superheated table only that we were using till now. 600 kilopascals, 60 degrees Celsius. This row, sorry. Right. Let me write down the data. Small v1 will come out to be 0.06023 meter cube per kg. U3 will come out to be 304.91 kilojoule per kilogram at 2. Our pressure has now reduced to 400 kilopascals because energy will first go away from the pressure because it can't go away from the volume. And our V2 is still the same as V1 because the piston cannot move yet, or in this case it has just started to move. And finally at state 3, our pressure is 400 kilopascals. Our V3 is half of V1 or half of V2 since V1 and V2 are the same, and it is 0.030115 meter cube per kg. So again we will have to determine the state at 3. Let us quickly do that. As P is given, we will draw the TV diagram at 400 kilopascals. We will try to see the values of Vf and Vg. However, if we will go back to the table, we will see that the pressure value is given at 399.6 kilopascals. Now, one option is to use this 399.6 kilopascals. It is a very good approximation, you can totally use it, there is no problem in that. But here I want to show you a different approach of the superheated table again. So, if we go to the 600 kilopascal superheated table, what we will see is that the Vg value, these are all Vg values or Ug values, right? Because this is superheated table, and as only a gas can be superheated, it is very obvious that all of these are G values, right? Vg value is 0.064. So in this case it doesn't really help us, right? What I was hoping for, if our Vg value was sufficiently low, what we could have done was that it would have been come out to be superheated vapor anyways. But since that is not happening, the only alternative left is to use the 399.6 kilopascal value. So if we use that, we will see that our Vf is very low and our Vg is this one that we just saw, and our V given is 0.03 and it is lying between this. So very easily we can say that it is a saturated mixture. Right. So if as it is a saturated mixture, what we will do is we will find the value of x. V3 equals to Vf plus x Vfg, and all of these V values we will use at 20 degrees Celsius, 399.6 kilopascals. You can always linearly interpolate all of these values between 399, between like 20 degrees, 15 degrees, 25 degrees. Between all of these you can do it as we have been doing, but that is cumbersome and that is not really expected, right? So 399.6 kilopascal is a good enough approximation for now, and using that we will get Vf will come out to be 0.030115. Sorry, our V given is this 0.030115 equals to 0.000803 plus x3 0.06440, and x3 will come out to be 0.4551, which means our gas is somewhere on the middle of this line. Important to know for when you are drawing the state diagram. And similarly, now we can find a u3 uf plus x3 ufg, again using the ufg and uf values at 399.6 kilopascals instead of linearly interpolating every time. It will come out to be 27.92 plus 0.4551 into 218.07. It will come out to be 127.163 kilojoule per kg. This time around I'm not going to be solving this equation. Delta Q equals to delta U plus W. I fully expect that we'll be able to find work, find delta U, and find delta Q as a result. Now let us look at the final temperature, right? Because that is also asked. Work you will be able to find, heat you will be able to find, PV diagram. Okay, in this question PV diagram is asked. Okay, so I'll do solving for that also, and final temperature also. So let us find the final temperature first. Now we can always say that the final temperature is minus 20.20 degrees Celsius, since we're using all the values at 399.6 kilopascals and the corresponding saturation temperature is minus 20 degrees Celsius. But do not do that, do not ever do that. To find final temperature or the final pressure, always linearly interpolate. Even though we are not interpolating with UF and UFG values and VF and VFG values, for final pressure and temperature, always linearly interpolate. So our Tp is at T of minus 20 degrees Celsius. Pressure is 399.6 kilopascals. At some temperature we don't know, our state 3 pressure reaches 400 kilopascals. And at minus 15 degrees Celsius, pressure is 480.4 kilopascals. So we will do y minus minus 20 equals to minus 20 minus minus 15 upon 480.4 minus 399.6 into x minus x1. Upon solving, you will get y to be minus 19.975 degrees Celsius, or T3 to be minus 19.975 degrees Celsius. Now we are asked the PV diagram as well. So we will have to find the value of x at state 2. X at 2, what is it? If we see carefully, then our pressure is 400 kilopascals, and our Vf at 400 kilopascals, we can use again 399.6 kilopascal value is 0.000803, and Vfg is 0.06440. So V2 equals to Vf plus x2 Vfg. So our x2 will come out to be, let me just calculate it for you, or do it yourself. Either way. 0.06023 minus 0.000803, okay, divided by 0.06440 is coming out to be 0.9227. Now I'll tell you why this is important, right? So let us draw our TV diagram. TV. So let us draw our initial pressure line of 600 kilopascals. Our 600 kilopascal line is somewhere over here, and initially it is a superheated vapor. So anywhere on this part of the line you can pick a point. Let us say that this is state 1 and this pressure is 600 kilopascals. Then at state 2 and 3 the pressure becomes 400 kilopascals. So the line will be drawn below the 600 kilopascal line, right? So this is our P2 equals to P3 equals to 400 kilopascal. Now where is the gas at state 2? That is what the quality factor will tell us. The quality at state 2 is 92%. And if you remember, higher quality means more towards the gas side, since intuitively quality means mass percent of vapor. So if high quality is there, that means there is more mass of vapor. So it will be somewhere over here. It will be closer and closer to Vg value. Right. And at state 3, we see that the quality reduces to 45%. So the mass of vapor decreases. So it will go back on this line and it will go close to half of it. This is the half point. This is x equals to 0.5 and it will come out to be somewhere over here. Therefore, our final TV diagram will look something like this. Starts from superheated, goes to a quality of 95%, then goes to a quality of 45% in this direction. Always remember these arrows. So that is why finding quality at intermediate state is always required when you have to draw a TV diagram, because then you'll not be able to tell what the state is at 2. And as we found here, at 2 it was higher quality and then the volume increased and then it became lower quality. Sorry, the volume decreased and then it became lower quality. So that is why we had to find the quality at 2, and that is why quality factor will tell us where on the saturated line will the mixture lie. I think after this we have 2 more questions, so let's get to it.